In this video I'm going to talk about three different models of Heathkit digital volt-ohm meters, or VOMs. These three are all part of a family which is unique within the Heathkit product line. They're neither the earliest models of Heathkit digital meter nor the last, but they all share the same basic design, and it's an unusual design, works reasonably well, but they're all very low-end meters, so their specifications are not that good. They're all 2.5 digit meters, which even for the day was not especially good. With such low resolution, it's hard to get accurate readings on much of anything. But still very interesting, and it illustrates how Heathkit tended to milk certain designs as long as they possibly could. So I'm going to start out with Chuck Penson's excellent book on Heathkit test equipment and go to chapter 3. Heathkit's very first digital multimeter, or digital VOM, was the IM-102, which I'm going to cover at the end of this video very briefly, but it's not the subject of this video. It used a Nixie tube display. It was a 3.5 digit display, which means it can display up to a count of 1,999, and it had pretty good specifications for the time. Was sort of a semi-pro level piece of equipment, and it was introduced in 1972, and they made it for several years. The subject of this video, however, begins with their product that they also came out in 1972, the IM1202. This was also a Nixie tube multimeter, digital multimeter, but it was only 2.5 digits, so it could display up to 199. And since the 1 is only used for half the range, you're trying to work with a resolution of only 2 digits, which doesn't allow for very much accuracy. On top of that, the meter only had about 1% accuracy, which again is not great. So couple that with the low resolution, and it's the kind of thing only a hobbyist might use. Certainly not a very good meter for use on a laboratory bench or any professional application. Still, at the time, the price point was attractive, because in 1972, to get a digital multimeter at a affordable price for a hobbyist or home user, I don't think there was anything competing with this. It was introduced for Christmas in 1972. It's compact. It has the so-called new look styling with the tan beige color scheme and those fairly nice looking knobs that series had. Pretty nice case, nice look, and then they went and cheesed out on some things. There's cardboard panels cut out of the box it came in to use as insulators, and cost-cutting things like that. Using a neon bulb for the 1 on the left-hand position of the display instead of putting another Nixie tube in to get that character. Just things like that were really odd decisions, but they're the ones they made, and they're part of what makes this series interesting. Now, the IM1202 was replaced 3 years later in 1975 by the IM1212. It's really just exactly the same design of circuitry, same specs, same parts. They even have the same part designations as the 1202. They just repackaged the circuit into what at the time they thought was a more modern enclosure. And they also did a cost-cutting move, trying to get the price down. By this time, 1975 and thereabouts, there were getting to be more choices for the hobbyist. You could get other digital multimeters around that time, and so Heath was trying to cut corners here and there. One of the things they did was left out this toggle switch here, which is plus and minus. It's the polarity reversal switch. It allows the plus and minus leads to be swapped internally. So if you're measuring DC voltage or DC milliamps and you've got the polarity backwards with the test leads, you could just throw the switch and reverse it. They left out the switch here, but the rest of the circuit is just the same. I don't think it's as nice a looking unit either. Now, one thing that is interesting about this is that this model was made for at least 2 different technical schools, such as Bell and Howell. I don't remember which other models this one came out as, but suffice it to say it was attractive to some of these tech schools, and they had their own versions of it. They even said Heathkit on the back. The only thing that changed was the paint on the front would go from white to perhaps a silver color on the Bell and Howell, for example, and they would change the Heathkit name and the model number to whatever the trade school wanted to call it. But everything else was exactly the same as the normal IM1202. Now, 1 year later, 1 year only, they introduced the IM1210, which is really, again, the same basic design, but somebody sharpened their pencils some more. I think that the main thing they were trying to do was dump the Nixie tubes and modernize the product by going to LEDs, but they also put it in a plastic case, and they did a few other things to cut costs further. The circuit, even though it's the same circuit design as the 1202 and 1212, they left out some extra parts. I would call it the Muntz treatment. And if you don't know who Muntz was, that was a brand of radios and televisions back in the early tube era. And the owner of the company would have his engineers design products that were competitive with the other companies making similar products. And then according to the story, he would go through and just randomly start cutting parts out of the circuit. And if he didn't see any change in the quality, the performance of the unit, the sound if it was a radio or the sound of the picture if it was a television, then the engineers were not allowed to put that part into the production models. So what essentially happened with those is that they performed adequately if they were in an area where you were near the transmitter and you had nice strong signals. But if you were in a more questionable area or had to deal with weaker signals, those extra parts that were cut out might help stabilize it or add some extra selectivity or something, and all of a sudden they would perform very poorly. But the Muntz units cost less. So I'm saying that because Heathkit did the Muntz treatment when they came out with the 1210. They took the circuitry of the 1212 and just started lopping out parts that weren't strictly needed to make the thing work, but which improved it in various ways and made it easier to calibrate and so on. However, at the same time, Heathkit made a couple of improvements on the 1210. They added a couple of circuit elements which were not in the earlier models. One of them was they recognized that both the 1202 and the 1212, if you got the polarity backwards, there was no indication that the polarity was backwards on the display. You would get a reading just like it was working normally, except it would be a nonsensical number. And if you weren't savvy enough to realize the number was nonsensical, you might take it as a valid reading. Both of these meters had an overrange indicator, but they did not have an indicator to say that the reading was bogus because you had the polarity backwards. With the 1210, somebody wised up and realized that for just a couple of extra parts, they could detect when the meter was reading a bad value or was about to read a bad value due to reversed polarity, and they would blank the display and light an indicator to say that your polarity was backwards. So you knew that you had to swap the leads and you were not presented with a bad value on the display. They could have done that just as well on these other models, but It was only finally introduced on here. At the same time, calibration is more difficult. All the trim potentiometers are much more sensitive because the spanning resistors were left off. There's a number of things like that done on it, but still an adequate low-end meter. However, by 1976, the price of $67.95 was becoming uncompetitive with meters that were better. And I have a video on a meter that came out, I want to say in 76 or 77. I think it was maybe 77. It was the Sabtronics multimeter. You can again check out my video on that. That was one of the first, if not the first, really affordable, high-performing digital multimeters that had specifications similar to lower-end commercial units. So by that time, this meter was looking kind of crummy by comparison to some other things you could get. Well, it lasted actually until 1982, but from what I've read in various places, the numbers were not very good on the sales of this unit. So, you know, its days were numbered, but they still milked it out. It may have actually been where they made a production run and then couldn't sell them and just kept them in the catalog until they finally sold out. Heathkit would do that, of course. Keep selling models long past their sell-by date until the stock was depleted. Anyway, so my video here is going to focus on the 1202, the 1212, and the 1210, and then I'm very briefly going to talk about the 102 at the end of the video, just because it's in the same time frame, even though the circuit philosophy is different, the specs are all different, and the design is overall entirely different. Okay, this is the Heathkit IM1202, the earliest of the related meters. It's really just like the others in features and ranges, except that it has this additional polarity adjustment switch which flips the common and voltage input leads around, so you don't have to swap leads for DC volts. But I'm trying to remember, I think it may also swap the DC milliamps. Certainly doesn't work on AC, that wouldn't apply, and it doesn't work on ohms. I think it does work on both DC milliamps and DC volts. For some reason they decided that was too expensive or not worthwhile having on the later model. Now, I haven't been able to keep this in cal. It's so touchy. You know, the components are old and everything. I've cleaned it up, but it's still kind of So I'm really just going to demo it to show how it looks, not to try to show it working well. So I'm on the 2 volt range. I'm off. I'm going to turn it on. And it comes up like this. Let me connect it to my power supply. Power supply on at 0 volts. I'm in milliamps mode. Duh. Put it in DC volts mode. Okay, so that switch is kind of iffy too. So it wasn't quite in the plus. I had to wiggle it back and forth a couple of times. So let's try taking it back down. So it's got a capacitor across the DC line. That's why it's slow to respond. They got rid of that in the later models. So that's 1 volt. It's not too bad here. 2 volts, and it gives me an overrange. Have to go to the next range. It's reading 2 volts. Let's go up to 9 volts. Not too bad. 8.8. That's 14 volts, reading 13.7. That's 19, reading 18.6. 20's reading 19.6. 21's Overrange, have to go to the 200. And it's pretty good. It's reading 20 for 21. 30, it's reading 29 for 30. And my power supply maxes out at 32 volts, so I'm back down to 0 volts. Okay, I've hooked it up in series, and the plug is moved to the milliamps ohms position. I'm in DC milliamps, 20 milliamp range. I've got my 4 to 20 milliamp tester in the circuit. I've got my power supply. I'm cranking it up to 24 volts, turning the power supply on, and I'm reading 12 milliamps, which is spot on mid scale on this. I'll flick it down to 4 milliamps. It's dead nuts on. And going up to 20, it's slightly over. The calibration on this isn't quite as good at the high end. But if I take it to the next range, it's showing a nice 20 milliamps. So, go back to here, take it off the 100%, we're back to 12 milliamps, working well in milliamps mode. Okay, I've got it connected up to my Variac. I'm in volts position on the plugs, AC volts, 200 volt range. Okay, turning the Variac on. Let's see what happens when I ramp the voltage up. There we go. It's about 50 on the Variac, reading 48. It might be a little low. That's more like 50. It's still reading 48 or 49. It's about 100 volts, reading 99. That's roughly 120 volts on the Variac. Spot on here. This is a really nice looking meter. I always thought probably the best looking one in the series. Some dust on there. Nice looking package, kind of classy. So here's a quick view inside the 1202. The main circuit board here. You get to look at the back of it. All the pots are on the other side, but you just stick the screwdriver through the holes that are adequately marked. Makes it fairly easy. Test points are right on the back for example, AC cal test point right next to the AC cal adjust, and the different ohms reference values, and the DC cal test point, and then all the other adjustments are up here. Well, my camera battery died just as I was finishing up this video. And since I'm packed for a trip leaving early in the morning, I have my other cameras already packed, so I'm not going to go digging up a battery for that. So I'm using my cell phone to finish this. So I think I already covered the back of the circuit board with all the adjustments. I don't know exactly where the video cut off, but I'll just recap it here. The pots all stick through the back of the board. Nice and easy to get at. Everything's marked, all the test points and reference points. Looking around the side, it's kind of a rat's nest in there. At least the fuse, or fuses, a fuse. I don't know where the other one is. Oh, it's right here. That's the line fuse down there. And then this is the fuse for the milliamp range. And this is the logic board stuck in there. It's at a bit of an angle. It's leaning backwards a bit. And it solders on kind of kludgely. This camera doesn't have a macro as good as my other camera. What's this pot? This might be the oscillator adjust. Not sure what that pot is. Anyway, so the two Nixie tubes for the Overrange and one are stuck in here. The yeah, there's actually 2 additional Nixie tubes. It's a little hard to see, but right there about in the middle of the picture behind the black object, you can see the top of 2 more Nixie tubes. Those are the extra Nixie tube, or not Nixie tubes, what am I saying? Those are the 2 extra neon bulbs for the plus and minus indication that you can kind of see there. Something the other models didn't have. That goes with the switch here. And then the Nixie tube right there for the overrange. And the Nixie tube, again, it's not the Nixie tube, it's the neon bulb for the overrange is right there. And then back behind those other neon bulbs is the other vertical neon bulb for the 1 in the most significant position. You can kind of see it right there. Yeah, you can. And then the 2 Nixie tubes are there. And those are both visible in here. This is very typically Heathkit there, just a piece of cardboard used for insulation. And there's the other side of all those trim pots jammed in there. And again, the logic board is called the logic board because all the logic ICs are on it. Jammed in there pretty tight. And then the main board is got all the other stuff on it. The switches, the back wafer of each switch is soldered directly to the board, and then all the other positions are wired down to the board. There's the plus and minus switch, the polarity reversal switch. This big transistor here is the Darlington for the plus 5 volt voltage regulator. It's the series pass transistor. Where else can we go on this? Oh yeah, the power transformers jammed in there. This is one of those things you do not want to have to work on once it's assembled. It would be a real nightmare to try to work on it. So nice cosmetically, but ergonomically, from a repair standpoint, it's probably the hardest of the series to work on. Still, I think a very handsome unit, and this one works well. I'm fortunate. I bought it from a seller, an eBay seller in Canada, who said it was clean, fully functional, fully tested, and operational in every way. And he was correct. I actually did tweak just one setting slightly, but everything else was there. So I didn't have to do anything to it at all. Very fortunate on that. So I finally got this IM1202 working and calibrated. It's actually made out of pieces of a couple of other meters. The case came from a different one from what the circuit board is, but then a couple of the other parts came from the one that the case came from. And over here I've got the circuit board with the transformer hanging haphazardly off of it. From the one that the case originally went with. This one was more dead. It has some burned out resistors and possibly some other damage. The main problem this one had was dirty switch contacts. The ICs needed to be pulled out and put back into their sockets to make good contact. Some of the pots were dirty and needed to be exercised a bit. And all these little wired jumpers that are removable for testing, about half of those weren't making good connections, so I wiggled and inserted and removed and did that a few times till they made good connections. And then the only remaining thing that was really not working was the right hand Nixie tube. On some digits was nice and clear. When it was changing to other digits, it seemed like it was trying to turn on several segments at a time. And at first I thought it was a faulty Nixie tube. Since they're in sockets, I just swapped them and it followed, or it did not follow the tube, it stayed with this digit. So then I tried putting the original tubes back, and then I tried swapping the 7441 open collector driver chips, and it followed the chip, so it was a bad chip. And I have it here, it's bad. The 7441s are a little hard to get, but I was able to find an original new old stock example, which has been put into this socket here. And now that's all working. I went through the setup procedure, and it is a remarkably, I don't know, a little vague or confusing in spots. They could have used better language and a couple other things to make it clearer, but eventually I muddled through it and tested it on DC milliamps. I didn't have a handy AC milliamp source. I tested on DC and AC volts and on resistance, and it was operating within specifications. This is not something I plan to actually use. I have many more meters that are better, but I am trying to make a collection of all of the digital multimeters that Heathkit had. At least the ones with Nixie tubes are interesting technology. I may not get every last model, especially the newer ones. I have less interest in those. Here's the Heathkit IM1202 in its Bell and Howell School's livery. It's just the paint scheme on the front panel that's different. The Heathkit one would have been white with black trim and had the Heathkit logo on here, plus the IM1202 name or model number. And the Bell and Howell version just says Digital Multimeter. All the graphics over here are just the same. And they have this kind of frosted silver paint finish that probably doesn't show up that clearly in the video. My understanding is these were still built from the Heathkit manual, and they still have a Heathkit sticker. The subterfuge of the rebanding vanishes right away. The 1212 does have these kickstands that pop up from the feet on the bottom. Okay, so let's fire this guy up. This should be... There we go. Fairly nice display. But even with the feet, it doesn't tip up enough to really see it very well. So, I've been using a block of wood under the left foot to get a reading. So I'm in the DC volts range, or DC milliamps. I should go to DC volts. The order of the functions is different between the different models. There it goes. It settled into 0. These do take about a 30-minute warm-up. All of these in this series, the oscillator and so on, are not stable until I think it's really the oscillator. That's about the only thing that really varies. Is not stable until it's been on for a while. So let's hook it up to a power supply and see if it works. Okay, it's hooked up to my DC power supply. Turn the power supply on now. It's still reading 0.1 volts. I'm going to go down to the 2 volt range, and I'm going to crank the power supply up to 1 volt. That's not too bad. If I go to 2 volts, it should overrange, and it did. It's kind of hard to see it, but the word over does appear there. And then it shows whatever is in the lower register. So I have to go to the 20 volt range, and it's still reading, well, 2.1 volts. Let's go to 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and it should overrange here, which it did. Have to go to the 200 range. It's at 20 volts. It's a little bit off at this point. That's 21 volts. It's off by about a volt. I think the specs say it it's barely able to meet one count, so it's not surprising that it's off by one. Let's crank it up. This is 32 volts, and it's not too bad there. So the voltage is working on DC. Okay, I have it hooked up in current mode, but I have to move the positive plug to the milliamp ohms jack so that it's putting it through the shunt. And it's reading 12.1 milliamps, which is what it should read with my milliamp tester here in roughly the middle position. I can crank that down just a hair, 12.0. And now when I put it to 0%, that should be 4 milliamps. Pretty close. When I put the other switch up 100%, it should be roughly 20 milliamps. And it's over, but it's reading the lowest part of the display, so it's really trying to read 20.1. I can go to 200, and, well, it rolls up to 21 in this case, but still. So we're roughly mid-scale here, and I can crank my milliamps around from roughly 4 to roughly 20. And if I go back to the 20 range, it'll be a little better. So that's full scale, just a hair under it. So that's working pretty well. Okay, I'm hooked up to my Heathkit IM-102 resistance decade box. And let's go down to the 200 ohm range and put this in the kill ohms or 200 ohm setting. I'm on the ohms jack. It's reading 1 ohm, which this does have some residual resistance, quiescent resistance. So I'm not even going to worry about the lowest range. I'm going to go straight to the 10 ohm range. It's got about a 1 ohm quiescent, so it's reading 11 when it should be 10. This is 60, it's reading 62. Take that back down. Now this is reading, this is on the hundreds range, and I'm reading 100, so it's reading 101. I'm going to go to the next step, that'll be 200 ohms, and it'll overrange, which it did. So I have to go to this range, and now it's reading in kilo ohms, so it's reading 0.2 kilo ohms for 200 ohms. And if I go up to the next range, 20 kilo ohms, now I can, this should be roughly 2K here, so it's reading 2.1 K. That's working. Go to the 10K range. I'm getting 10.1. If I go one more notch, it'll overrange, which it did. Go to the next range here. Reading 21. That's not too bad. Go up to 90K, and it's right on. Of course, it's low resolution. And that's 100K dialed in. It looks spot on there. I'm going to go to the 2 mega ohm range, which is confusingly called 2K. So it's reading 0.1 mega ohm, which is 100K. And that's all working. It's all pretty close to where it should be. So the ohms range is working. Okay, I'm on the AC volt function. 200 volts selected. I'm on my variac with a line cord into the variac. I'm going to turn the variac on, and I'm going to watch my meter as I crank the variac up. That's about 50 volts on the variac. Roughly 100 volts on the variac. It's just bouncing around a hair. A little bit high. That's roughly 120 volts on the variac. It's jittering a little bit. So it's pretty close. I might be able to see if I can dial it in just a little bit. There we go. Make it a little more stable. And back down to 0 volts AC. So that's working just fine. So let's just do a quick what's what in here. So we have the AC line coming in here. There's the power fuse back there. And the power switch is up here on the back of the function switch. And the power leads run underneath the circuit board to go back over here. Power transformer. And then there are 3 power supplies. That's why there are 3 sets of leads. A red and black, 2 greens and 2 yellows. And each power supply is using a different mode. The 5-volt power supply for the logic uses a full wave rectifier using a center tapped secondary and 2 diodes and a voltage regulator, and here's the series pass transistor. And the plus and minus 15 volt supply for the analog circuitry is not regulated, and it doesn't really need to be the way it's being used. So it just has Zener diodes. I mean, I should go back. It's regulated to the extent that Zener diodes do it. It's not as tightly regulated as if it had a IC regulator on the plus and minus 15 volt legs, but it's still regulated. And then the high voltage supply for the Nixie tubes is really just halfway rectified, and that's about it, off of a fairly high voltage secondary. There are 10 trim potentiometers scattered around the board. This is for AC calibration. This is for DC calibration. This is for zero adjust. This is for adjusting the AC test point. This is for adjusting the oscillator frequency. And then over here we have the 2 meg, 200K, 20K, and 2000 or 2K and 200 ohm resistance adjustments. So it's pretty straightforward. There's a small analog section here with a single op amp, and that's only used for the precision rectifier for when AC measurements are being taken. The bunch of transistors that are along here form the analog to digital converter, and it's really just doing a slope comparison. So there's a constant current source in there. It's charging a capacitor at a constant rate, and then it's using simple transistor comparators to compare the input voltage against the slope, and when the slope reaches it, then it flips a flip-flop and changes the state of a counter circuit, and the counter circuit's over here. The idea is that the oscillator, which runs in here, and that's also transistor based, runs at a fixed speed, and depending how long the ramp takes to charge up to the input voltage each time it does it, determines how many counts from the oscillator get counted by the counter, and hence a larger readout. And then there's some more ICs that convert the counting to BCD, and then BCD to 1 of 10 open collector, and that's what's in here. And then there's a couple ICs that are just doing some glue logic and also comprise the flip-flop. Let's see, other than that, There are 5 resistors over here, precision resistors. Those are used for calibrating the resistance ranges. There's a couple test points, one for AC and one for DC, that are used in calibration. And that's about it. It's all self-calibrating in the sense that you don't need any extra test equipment to calibrate it. It uses all internal either Zener voltage references or precision resistor references, and it's supposed to be able to be calibratable within 1% of full scale. There's also 2 Nixie tubes over here I forgot to mention. The Nixie tubes are driven off of these 7441s, which are taking a BCD input and converting it to a 1 of 10 output, but it's a open collector output with sufficient voltage range to handle the voltage required to operate the Nixie tubes. So that's those 2 chips. And then these couple of transistors down here are what turn on these 2 neon bulbs, and the neon bulb here is positioned and sized so it's roughly the same height as a 1 would be on the Nixie tubes, and that's how they get the 1 in the 3rd digit. It can only be a 1, so it doesn't need another Nixie tube. They're cheaping out there. I wish they would have just put another Nixie tube in there and just had it read 1, but that's not what they did. And then another Nixie tube here is behind the words over on the display silk screen. So when that turns on, it indicates an overrange. This meter is not auto-ranging, so it's a little bit of a pain in the butt to use that way when we're used to these days having auto-ranging on meters. But that is actually pretty typical of the older, less expensive meters. So that's what's in here, and I'm going to button it up. Alright, for the IM1202, I've just finished calibrating it. I'm going to start out with the Ohms mode. I'm in ohms here. I'm going to go down to 200 ohms here, and it's 0 in all these settings, just the decimal point moves. And I have the test leads shorted out. I'm using my Heathkit IM1202 resistance decade box, and it's currently set to 0 ohms. So I'm going to go and crank it up to 1, and as expected it's off because there's residual resistance in here. So it's always off by a little bit. I'm going to go up to 10 ohms, and again it's off by a couple ohms as expected. That's 60 ohms, 83 ohms. Yeah, so it's off by about 3 ohms there. Now if I kick in the 100, it's going to be overranged pretty soon. That's 100 ohms plus the 2 residual. And now I get the overrange, so I have to go up here to the 2k ohm range, and it's reading 0.23, 3, 4, 5. I can go up to the 1k and make it 1k, and again it's off by a little bit. I'm quickly overranged. Go to the 20k range. That's supposed to be 7k there, so it's still off by a little bit, but the specs on this meter aren't that good. It's calibrated as tightly as it can be. And let's go to 200k and crank it up to 20k, 80k. It's responding well, but it's always got a bit of an offset. And finally the 2 meg range. This is 100k, 600k. So the tolerances are not great, but it is working otherwise pretty well. Okay, I have it set up for DC milliamps, and I'm on the 20 milliamp range. I have my little current loop tester here just as a simple source of milliamps. it's not actually the source, it's just a 2-wire transmitter, so I have to have a power supply. And I have my power supply set to 24 volts. When I kick it on, it should go to some value somewhere between, well, it should be ideally about 12 milliamps or thereabouts. Going to turn the power supply on now. And it's pretty close to 12 milliamps. Tweak the pot here to get it to be 12 milliamps. There we go. So that's mid-range in the 4 to 20 milliamp range. Now if I kick my left-hand switch on here, that'll put it to 0%, which is 4 milliamps. And it's pretty close. If I turn the 100% switch on, it should go to 16 or to 20 milliamps. And again, it's pretty close. There isn't actually a calibration for this. It's just relying on the tolerance of some resistors. It's basically using the calibratable DC volts range to read off of the unadjustable shunts. So I expect this to be less than stellar, but it's still pretty close. And now I'm going to relieve that, and I'm going to crank the knob here from 4 milliamps approximately. Responds pretty well. And up really close to 20 milliamps. Okay, I have it in DC volts range now, or in DC volts mode, and the leads are connected to my power supply, which is currently turned off, and it's set to 0 volts. When I turn the supply on, it's still reading kind of a overrange situation. If I give it 1 volt on the power supply, it's showing 1 volt here. It's going to peak out at 2 volts because I'm on the 2 volt range. So it's sitting at overrange, and it's bouncing around just above and below that value. I'll take it back to 1. Yeah, it's at 2 volts, so it's at 1.98. If I go to 3 volts, it's going to be overranged, so you get a garbage result. I have to go to the 20 volt range, and it's off by a little bit. 3 volts, 4, 5, 6, 7, 8, 9, 10. Giving it about 13 volts, and it's right on there. 14. That's 16 volts. It's going to overrange pretty quickly. That's 19 volts I'm giving it. And now I'm overranged. Have to go to the 200 volt range. And I'm giving it actually 22 volts here. Again, there's no calibration for this. It's relying on tolerance of resistors. I'm giving it 22 volts, and it's saying 25. I guess I could probably check this with another meter. There. Yeah, and it's agreeing that it's 22 volts, so the meter's not spectacularly accurate there. So I'm up to 28 volts, and it's kind of off here. But there's no trim pot for this, other than just the general DC volts, DC cal. I suppose I could try dialing it in ever so slightly, but I'm kind of scared to touch it because the adjustment's so touchy. Alright, so I max out to 32 on the power supply. I'm going to go down to 16, and it's reading 18, 13, that's 7. Yeah. But I'm in an awfully high range there, so if I go to a lower range, the accuracy gets better. Let me try touching that up ever so slightly. Again, we're on a different resistor here, so the tolerance is going to be different. I'm going to leave it there. It was just breathing on the pot, it moved that much. So I'm down to 2 volts. Let me put it on the 2 volt range, and it's pretty close. So I'm going to leave it there. I put it on AC volts and the 200 volt range. I have it hooked up to my Variac, and I'm going to see if I can get anything out of it. Yep, there's something. It's reading about 21 volts, and according to the Variac, it's about 20 on up to 50 there. So let's see. That's 50 on the Variac. That's working. That's 100 on the Variac. It's about 120 on the Variac, so that's working very well. Oops. Good response on that. Alright, so bit of an overview on this one. I'm going to put it back at the 20 volt range, DC volts, and then turn it off. So looking over the top, here's an overview of the circuit board. Okay, a couple of switches which are not on the circuit board. This is the range pot, or a switch which is a little bit loose. I need to tighten up the nut on the panel. It's always going to be a little floppy because it's only on a plastic panel. It's never going to be quite as firm as if it was on a metal panel, or on a metal piano, on a metal panel, that is. But the nut does need to be tightened up a little bit. So this is just switching between different routings for the input jacks, and then the shunt resistors and the voltage divider resistors are all on here for the different ranges. Compared to the earlier 1202 and the 1212, the design is simplified somewhat in that area, and they're reusing resistors from one function on another function, getting double duty out of them, so there are fewer resistors, and that probably compromises the accuracy a little bit. All of the calibration adjusts are along here, which is nice. They're all in a row, and except for the AC reference adjustment and the clock oscillator adjustment, which are over here. There are 3 7-segment LEDs on a secondary circuit board, and those are just tack soldered onto foils that go to the edge of the main board. There's no connector there. These ICs here are all of the digital ICs, really, except for the one here that's used for the clock oscillator, or I'm sorry, for the what is that? That's the 7402. So that's part of the reset circuit, actually. The clock oscillator actually uses transistors, so they're probably these guys over here. I didn't check to see which one's which. Your power fuse over here. Your fuse for the input is there. It's used on all ranges and functions. Your power supply components over here. There's a little dirt on the board. That's why there are some spots that are a bit darker. I didn't completely clean it off. When it came to me, it was quite dirty. It looked like it had been left open and put in a wood shop and then had mice living in it. So I did quite a bit of cleaning inside and out. The strain relief on this is kind of late Heathkit cheap. It's really just a knot, and then the cord fits through a notch in the case. Let's see, the ICs here are all the ones for the analog to digital converter flip-flops, and the counter chips, decade counter chips, and the BCD to 7-segment decoder driver chips for the display. The third digit is just run off of some glue logic. It's not run off of another stage of chips, and that's consistent with the earlier 1202 and 1212 with their Nixie tubes. It didn't use an extra set of chips. They just used, you know, a transistor or something to operate the one for the last digit. Down here are the 5 resistors. These are the reference resistors. They're not part of the normal circuit. They're just tied to ground on one end, and then they have little loops in them here to make easy clip-on points as test points. And those are used when setting up 5 of the pots along here. The circuitry for the AC converter, or that's what Heathkit calls it. It's really a op-amp precision rectifier circuit, and that's around here. It's based on that 1301 op-amp. And then I believe it's these transistors here that make up the analog to digital converter. It's all done with transistors and a few resistors, just like on the 1202 and the 1212. It's roughly the same circuit. They tweaked a little bit, but it's still all transistor based. This is the power switch on the back of the function switch. And let's see, all the power supply stuff is over here. Typical Heathkit, they always seem to have a power resistor somewhere that runs pretty hot and discolors things around it, but without burning up. It's just, they like pushing things to the limit. You know, if the calculated tolerance was 2 watts and they put a 2-watt resistor in there, they didn't care if it got too hot to touch, as long as it was within the specified not tolerance, but the specified specifications of the part. I remember I had a Heathkit oscilloscope that worked just fine, but there were some resistors very much like these, just carbon composition resistors, that were just slowly baking the circuit board beneath them, but Heathkit insisted it was fine, and they never did burn up or anything, so had to take them for their word on that one. So really that's about it for the inside. I should note that other than cleaning it up, prying the ICs out, it didn't work when I got it from the eBay seller. He listed it as non-working. He was the original owner. He even sent me a nice eBay message about his career in the military doing electronics and so on, and how he built this one originally and used it for many years, but then he opened it up for some point. Maybe he was going to recalibrate it or something, and then it just sat open and got full of dust, and he decided not to try fixing it. He was just going to sell it. I think I paid $19 for it, considered as a pretty good deal. Everything was in real good shape, just dirty. But as anything, these switches and everything sitting out in the air and getting dirt on them, the switches were making really bad contact, although not worn out, just making bad contact from dirt and oxidation. So the first thing I did was sprayed Deox on all the contacts of both switches and worked them back and forth a bunch of times. I exercised all the trim pots, wiping them back and forth, you know, probably 15-20 times each. I blew all the dust off and wiped a lot off with Q-tips. Took the case all apart, put it in a warm soapy bath, scrubbed it with toothbrushes, did all that stuff, went over it with alcohol wipes, cleaned the knobs. I don't know if I already mentioned that I pried all the ICs out of their sockets because Heathkit used kind of cheap sockets, and it would be expected that there would be some oxidation on the IC leads and or the socket connectors, so taking them out and putting them back in. And also there is these not test points, but they're jumpers that can be removed for testing parts of the circuit. I figured those are probably corroded, so I pulled them in and out of their connectors a few times. And let's see, so ICs, deoxed, cleaned and stroked the pots. I think that was it. There were no bad components, and it calibrated just fine, no problems. With that, it met all of the steps without any difficulty, but as I said, the tolerances of parts on this are not great. It's only a 2.5 digit meter with fairly low accuracy specifications. Very much a low-end entry level meter. Not that something you'd want to use for anything serious, but okay for a student maybe, just getting started and just doing some basic measurements for an economy price. These are not the original leads. These are some Pomona Electronics leads that I bought for it. A small alligator clip and a crocodile clip, whatever these things are called. It did come with the original probes, which I have somewhere. Yeah, here they are. But the pin is broken off of the plus lead, and the minus lead is really large and hard to clip onto a lot of electronic. So I figured I'd be better off using the newer Pomona parts rather than the busted up original ones. And there's a rear view. IM1202 serial number. The paper label here with the shock caution was peeling off on both ends. It was really just an old, I don't know, like envelope glue kind of adhesive which had dried out. So I tacked it back down with super glue. And here's the bottom. Got some air vents on it. And the top. And the front. Not a bad looking unit. I think it looks a lot less cheap than the Nixie tube version. Just so that I don't get accused of leaving something out, I thought I would do a brief mention of the Heathkit IM-102 Nixie tube digital multimeter that Heathkit came out with in 1972. I do have this one. It's actually the first Nixie tube digital multimeter of Heathkit's that I acquired. I've been sitting on it for years. eBay purchase, and the seller said it was working, but it's one of those things where somebody gets it at a rummage sale or an estate sale or somewhere and just sees that it powers up and says it's working. It clearly isn't, but parts of it are working for certain. This was Heathkit's more professional digital multimeter at the time they were doing Nixie tubes. It's also their first digital multimeter model, the first one they came out with. Nice looking unit. Seems a lot more professional than the other ones in this video, and certainly it is. This one hasn't been restored or cleaned up. It does power up, like I said. It's a 3.5 digit meter, but doing the typical Heathkit thing, you know, they could have put an extra Nixie tube in there and just used the one. Instead, they did their trick of putting a regular neon bulb in and have it fill in for the fourth digit, essentially the one that can either be off or 1, which is kind of crappy, but that's what they did. And it has plus and minus illuminations. The plus one's illuminated, and an overrange indicator, which, like the other ones in the Nixie tube series, is just powered or illuminated by the same kind of neon bulb, and is always too dim and misaligned and kind of barely adequate. They really could have done a nicer job, but they stuck with this dead horse. But just to contrast it with the other ones, even though this one is not working entirely, obviously a lot of it's working, but I've had it taken apart for years and just have been stymied because it's been repaired, and I'm not sure entirely repaired. It looks like it may have had some damage, and perhaps the previous owner started to fix it and gave up on it. Who knows? But it had some foils blasted off the board over in the area of the switches. It has, I don't know if these were original Heathkit sockets or not. They're not the proper sockets. They're the individual pin sockets. The chips are all quite old type, and I think they're in the 7200 series family. I don't even remember what that is, if it's RTL or something like that, a pre-TTL family. I haven't been able to get documentation for this yet. As a matter of fact, just was able to acquire a manual for it on eBay, which has not arrived yet. And so I'm hoping that that will give me enough information to troubleshoot this. But what scares me is there's a lot of really odd parts on it, like these, that look like they'd be unobtainium if they turn out to be bad. These old style CAN op amps, which if those are bad, they can be replaced, if not something with the same form factor, at least something functionally equivalent. If these things are dead, good luck. There's this, I don't know if it's proprietary or what, but it's some sort of hybrid package that does something. I don't know yet what it does. Probably need to recap this thing, but it seems to be working after a fashion. I haven't checked any voltages on this yet. Maybe the power supply for the analog circuit isn't even working. Maybe that's why it's dead. Who knows? But just to give an overview of what this thing is like, it has a much nicer chassis, which is a lot more like professional test equipment. It uses, I guess I'd call them nicer switches. They're more or less sealed selector switches. There's a lot more gangs on them. And they partially solder into the circuit board and partially have leads. Lots of fuses. Pretty decent double-sided circuit board. But again, if anything's bad in this switching area, it's going to be really hard to fix. Then there's this secondary board here. Again, I'm not sure what that is, but I do know that this model came with a calibrator built into it to get better accuracy in calibration than you could with just normal Zener references and so on that their other models used. So that may be the calibrator circuit. Not sure yet. There's more evidence of repairs on the circuit board, like somebody dragged solder around to fix something. The fact that there's apparently blown up foils on there suggested something was hooked up to this that was either on the wrong inputs or way too much voltage or something, and a lot of things could be damaged. Anyway, it still has things like the separate jacks for different functions instead of having switching, so that you don't need to do that. But there's an analog section, clearly an analog section over here. Somebody put on what looks like an aftermarket heat sink on. That's probably the 5-volt regulator for the logic. And the display drivers seem to work because it's reading out complete digits. The Nixie tubes seem to work. The neon bulbs in their little carrier work. Probably a lot of it's good. It may just be one or two parts that are bad, but if it's in one of these difficult to obtain parts or in the switching, I may just have to leave it unrestored. Anyway, that's what this animal looks like, in case there is no other representations of this one on YouTube. At least there will be this little bit of video showing what it looks like, if not functional. Somewhere I've got the rest of the case for this. I'm not going to focus on the manuals for these 3 meters as I've done on some of my other videos, but I am going to go over the schematics at the end of the video. However, I do have a reproduction purchased from a guy in Switzerland, I think, that is useful for nothing else than it has the calibration procedure for the 1202. I wasn't able to find a proper Heathkit manual, or an original rather. I do have an original manual for the 1212, and I do have an original manual for the IM1210. But again, other than the assembly instructions and some details like waveform pages and so on, I'm not going to dwell on what's in these manuals. It's the usual nice Heathkit manual in every case. The thing that's useful about the 1210 manual is that the circuit description is much more thorough and better written. The circuit description is not present in my 1202 manual. It's not a complete manual, it's just the calibration section. And the 1212, the circuit description is very perfunctory, and it's hard to understand how it works from how they describe it. But in the 1210, they go into considerable detail, and it obviously had a different author for the theory of operation section, or circuit description section. Now I have redrawn the schematics for all 3 of these models. I drew them in AutoCAD and tried to correct a lot of the failings that I would consider to be characteristic of the Heathkit original schematics. Number one, they're very tiny, except for the 1210, which was better drawn. Some of the text and so on was so small it's very difficult to read, and if you reproduce it, it becomes illegible. And then the layout of the schematics is poor. Whoever laid them out did not have a good knack for clear circuit diagram layout, so it was hard to understand how it worked. And there was also a lot of information just flat out missing, and the same problem affected both the 1202 and the 1212. So I did a lot of study in circuit tracing and peering at the original schematics through magnifying glasses and so on, and spent about a week on it. Came up with this CAD drawn schematic, which I'm sharing through my file share website, which I'll put in the video. Then I have the circuit schematic for the 1212 here. Same treatment. I basically just took the 1202 and made the changes necessary for those few changes that there are between the 2 models. And then finally the 1210, which even though the circuit theory is the same and the basic blocks of the circuit are the same, because they did so much cost cutting on it, there are still a lot of differences. And so I adapted the 1212 for the 1210 and just made a ton of changes. Probably only actually kept about half of the original drawing by the time I was done. Of course, the display section on the 1210 is different from the other 2 because it's an LED display. But I'm going to use the 1210 as the basic description to go through here. I'm going to spend most time on this one. So let's start out with the power supply. Just a normal dual winding transformer, so it can be connected with windings in parallel or in series for 120 volts or 240 volt operation, fuse and power switch. Then there are 3 windings on the secondary side, the first one of which is center tapped, and the center tap of this winding is common with one side of this winding, and that's referenced to ground. Now both of these models, the 1202 and the 1212, have metal cases which are earth grounded through the power cord, whereas the 1210 has a plastic case which is not grounded, and the only thing that's grounded to earth on it is the core of the power transformer. But on the 1202 and the 1212, the chassis ground or earth ground is connected to the circuit ground through a high voltage capacitor. So if you did get some short circuit from the power lines, for example, to the case, it would be shunted to ground through that capacitor, but otherwise the two grounds are isolated. So let's start out over here with the input circuit. There are 3 jacks for voltage, common, and milliamps and ohms share a terminal. The milliamps and ohms have a fuse, whereas the voltage jack does not have a fuse. I won't follow every line through the switches, but there are the 2 switches, one for function selection and one for range selection, and they each have several gangs arranged here. So this model, being the 1202, also has this switch. This is the polarity reversal switch, and that's interjected between the first gang of function switch and the second gang of function switch wafers to reverse the polarity. And there's a third gang which is doing another function there, and a fourth gang of the same switch which is used to operate 2 neon bulbs on the display to tell you whether you're in reversed mode or not. Starting out with the voltage, when we're in the voltage mode and we select, for example, DC volts or AC volts, we go through the polarity switch, we come out through this gang and then come up this way, and we go into this voltage divider. This is the voltage range selection switch. So the incoming voltage is applied to this resistor ladder voltage divider, and then the range switch picks off various points in the voltage divider so that you get a roughly 0 to 2 volt range resulting coming out of the switch. And then, depending on whether it's AC or DC, the signal may be routed down through this circuit, which is the AC converter circuit. In that case, if it's AC coming in, it converts it to DC and routes it back. And then finally, the DC volts comes to this final gang on the function switch and is presented to the analog to digital converter. If it's coming from the output of the AC converter, then it comes up this way and is picked off and goes into the analog to digital. Now if you're going to do amps, we come in here, we go through the fuse. Let's say we're taking DC milliamps, go through polarity reversal, come out of DC milliamps here, follow this up, come around, and it's presented to this switch and then goes through that, comes into here and goes to this switch, and it's presented to one of several shunt resistors which go back to ground, and that's of course where the other lead is plugged into, because the common terminal, once it's been polarity flipped, essentially goes to ground right down here. So what you're essentially doing is taking the incoming current and passing it through a shunt resistor and then back out, and then that develops a voltage across it, which is picked off here and run up to this switch and then through into the analog to digital converter. If it's an AC milliamps, then it's routed first through the AC converter, back through here and into the analog to digital converter. Finally, for the ohms, we have this constant current source. And a common way of doing a constant current source is to use a Zener diode feeding the base of a a pass transistor and then feed one side of the pass transistor with a resistor which controls the current, and then through the transistor you have a constant current as a result, and that can be used by other circuitry. So they're using that fairly classic circuit, but on here, instead of using a Zener diode, they're using a reverse biased transistor with one lead cut off, and they're using that in place of a Zener, and a normal bipolar transistor will do that. And then it goes into the pass transistor. There's a couple of diodes there to protect the circuit in case of reversed polarity. And then there are 5 different resistors that can all be dialed in with trim potentiometers, one for each of the 5 ohms ranges. And then the result of that is that you have a fixed constant current coming out of the collector of this transistor, going up this way. It goes into the ohms part of the function switch, and it comes out and it makes its way back to the jack here, goes out through whatever resistor you're trying to measure and back to ground. And in the course of doing so, it develops a voltage across it, a DC voltage. The DC voltage is proportional to the resistance because the current is constant, and then it's eventually passed up here to this switch and once again presented to the analog to digital converter. The entire goal of all these switches here and this constant current source and all these switches up here is to take whatever we're measuring, voltage, current, or resistance, in whatever range we're measuring, and it converts it into a low voltage swing. Again, I don't remember exactly what it is. It may be just 0 to 2 volts or something, a fairly small span of voltage, because the analog to digital converter is only designed to work with a small input voltage range. The power supply needs to develop 3 voltages, actually 4 voltages, come to think of it. It needs to provide a 5 volt source for the TTL logic ICs that are primarily in the counting circuit and the display circuit. It needs to provide a plus and minus 15 volt bipolar regulated voltage, which is used really only for the AC converter and the analog to digital converter. Very low current, but it does need the bipolar supply. And then finally it generates a high voltage source. The transformer secondary is 250 volts AC. It's half-wave rectified, but not filtered in any way, so it's still a fairly high voltage, and that is used only for the neon bulbs and the Nixie tubes in the display. Let's look at the full wave rectifier on the 5 volt supply. It's not a bridge, and it doesn't need to be because it's not developing a bipolar supply, and it has a center tapped transformer to work with, the center tap of which is grounded. So all you need to get full wave rectification is 2 diodes coming from either side of the winding. It's filtered with a 1000 microfarad electrolytic and then applied to the series pass transistor on its way out to the 5 volt supply. Now it's a Darlington transistor, so it's got one transistor driving another in the same transistor package, but that needs a control voltage to cause it to produce 5 volts, and the way it gets that is from the bipolar supply. So let's look at that. This one is not center tapped, which is unusual for bipolar supply, but not unheard of. It's half-wave rectified, and it can get away with that in a small value filter because the current demands are so low. So even with half-wave rectification and a small filter cap, you can still get a constant or a smooth voltage out of it. Then there's a dropping resistor or current limiting resistor, followed by 2 Zener diodes in series, 15 volts each, So you end up with 15 volts across this one, 15 volts across that one, and the remaining voltage is dropped in this resistor. Then there's a small filter cap across each zener, and the point between the zener and the filter caps is referenced to ground. And that's why this, instead of being a 30 volt power supply, is a plus and minus 15 volt supply, because of that ground reference in the middle of the two zeners. Now you want to have some sort of a load on this, and the load on the negative side is just this 1K resistor. In the case of the positive supply, it doesn't need that because there's this circuit acting as the load. So let's look at what gets done with that. Besides going to the ICs and other analog circuitry, the plus 15 volt supply comes up through a resistor and then a 6.2 volt Zener diode. So you get a regulated 6.2 volts here. That's filtered by this 47 microfarad tantalum capacitor and presented to the base of the Darlington pass transistor. Now, with the double base to emitter drop of the Darlington, you subtract that from the 6.2 volts and you get 5 volts. So that is what the output is, and it's reasonably well regulated. There's no actual feedback, but it's because of this design, it works adequately well. Now there's also a voltage divider off of this 6.2 volt reference, and it's a roughly 2:1 ratio, and the center point's tapped off as the DC calibration test point. So that's a known DC voltage, and it's used during calibration so you can calibrate the meter without having any other meters or test equipment to do it. Likewise, the 250 volt circuit down here for the high voltage supply is divided down by two fairly high value resistors on either side of a trim potentiometer, and that provides the AC test point. Now, a clever thing that's done here is they know the ratio of what these two voltages should be. So this one is fixed, this one is adjustable, and you adjust it to match that one while using the meter that you're trying to calibrate to do the comparison. But because the ratio of the two is something they can calculate, it's possible to simultaneously be calibrating this test point while calibrating the meter. So it's an interesting process of calibration, but it does work. So now let's look at the AC converter. This is what converts voltage dropped and conditioned voltages coming from the switches for any of the milliamp or voltage inputs. So by the time they get to this point, they've all been adjusted for range, and if it was a current, it's already been dropped across the shunt resistors and a voltage developed. So you have a voltage in a small voltage range applied to this circuit. First thing off, we get rid of any DC component that might still be there. It has to be an AC signal that's applied to this AC converter. If you apply DC voltage to it, you won't like what you get. So we drop any DC that might happen to be there. Then we have a dropping resistor and a pair of clamp diodes. Now the clamp diodes, instead of being tied to plus 15 volts or minus 15 volts as they could have been, they're connected to voltage dividers instead with a 2:1 ratio, 10K over 4.7K. So you have roughly 5 volts at this point and roughly minus 5 volts at this point. So you're clamping the input within a range of plus or minus 5 volts. On the 1210, that's one of the things they got rid of. They said, you know, we don't actually have to clamp it to plus or minus 5 volts. It'll be fine if we just clamp it to plus or minus 15 volts, and we can save money by leaving out 4 resistors. So that's one of the cost-saving moves they did on the later model. Then we have to bias this FET to ground, and here it's done with this elaborate 3 resistors essentially and a capacitor. And on the later 1210 they decided all they needed was 1 resistor. They could get rid of 2 more resistors and a capacitor. They were not needed. But essentially that biases this into a good operating point, and then you apply the range limited AC voltage to the gate of this FET. And when the FET is configured in this way, since the FET is a voltage controlled transistor, unlike a bipolar transistor which is current controlled, this acts as a simple buffer circuit or a follower. It allows the input signal to be passed to the output, but the output is low impedance and the input is very high impedance. And the reason this is here is in large part to allow the highest possible input impedance to be presented to this whole switching network out here. So we end up with a conditioned, range-limited, buffered AC signal, which by the way is presumed to be a sine wave. This circuit is really not the most elaborate possible AC converter that some nicer meters might use. It's really intended to work with sinusoidal input waveforms. It'll work if you give it other waveforms, but the result will not be as accurate. Once again, we have a couple of clamping diodes to keep the input voltages between the plus and minus inputs within a very small range of each other. And they should be, because an op-amp, which is what this is, with feedback, should always have both inputs at the same voltage. And if they're getting outside of that, then the op-amp can't function correctly. And so some designs will put these clamping diodes in there to force the common mode voltage between the 2 inputs to be very small. This is something else they got rid of on the later design. They figured they didn't need them and they dumped them. But all 3 meters use the same circuit here. This is just an older op-amp, the LM301, originally I think a National Semiconductor part, or maybe it was Fairchild or somebody and incorporated into National Semiconductor, but the LM prefix is a National Semiconductor prefix. This is a stabilization capacitor on it. Later op-amps didn't need that. The op-amp itself is powered from the plus and minus 15 volts. And this circuit here is a classic circuit for a precision rectifier circuit, which is, if you try to rectify a signal using diodes alone, then you're always going to have an inaccurate signal, because the diodes won't start working until you forward bias them beyond their dropping voltage, their forward voltage drop, in other words. So at the low end of the signal, you're always going to have a bad signal or an inaccurate signal. So how do you fix that? Well, you put the diodes into the feedback of an op-amp in such a way that the action of the op-amp removes that issue with the diodes. I won't get into how that works, but this is just a textbook circuit here. So this resistor is in the simple negative feedback path, and this just provides a known DC reference point for the op-amp to work at. And then these 2 capacitors, these diodes, this resistor, or these 2 resistors work to provide feedback in such a way that it negates the forward drop of the diodes. And at the output here you end up with a DC voltage which is the same as the RMS value of a sinusoidal AC wave coming in. And that's why I said this works primarily with sinusoidal waveforms. If you give it a non-sinusoidal waveform, the output will not be the true RMS value of the AC. But if it's sinusoidal, it'll be pretty much the true RMS value in a very simple circuit. Finally, this resistor to ground here allows us to calibrate the converter a little bit, so we can dial it in to be exactly the right value. So we end up with an AC signal coming in, a precision rectified DC signal coming out. There's a simple filter here to remove any additional ripple that might be there. And then the output is presented back to the selector switch, and it goes into the analog to digital converter. Now I have to jump ahead. I want to go straight into the analog to digital converter, but to describe it, I'm going to have to start out with the downstream circuitry so that this part makes sense. Ultimately, digital meters are counting. At some level, they have a counting circuit which during a specified period of time is counting up a number of pulses, and at some point, depending on the voltage, it's not allowed to count pulses anymore. So it'll count a lower number or a higher number corresponding to the input voltage. So what we have here is a couple of 7490. These are just decade counters. So you present an input signal, which is a clock signal, and it counts up to 10 and then resets and counts up to 10 again, keeps doing that, and every time it overflows and resets, a signal comes out of here and goes into the clock of the next one. So this one counts units. Every time it rolls over, it's just like an old odometer on a car. Every time this one rolls over, this one counts one more notch or one more tick. So this is the tens. Now this is a 2.5 digit meter, so it actually can count into the hundreds, but all it can do is count to 100 and no further. Meanwhile, this part can still count up to 99, so the highest count is 199. But Heathkit kind of cheaped out here, and instead of using another decade counter for the third digit, they didn't use the L or the 7490. Instead, they used a flip-flop. So the overflow of this one comes out and goes into a flip-flop, and when that flips, it acknowledges that this one is overflowed, and its output turns on. It turns on a transistor, turns on a neon bulb, and that's the neon bulb that's used to represent a 1 in the hundreds place. Now, if that happens again, if this rolls over one more time, so it would be trying to roll over to 200 instead of 100, now the next pulse comes through and it ripples through here. This is a ripple counter. And so now this guy turns on, the Q of this one turns on, and instead of this lamp being turned on, it turns on this one, and this is the neon bulb that's used to indicate an overrange. So that's the way that's done. And every once in a while you have to reset these counters every time you want to take a new count. So there's a reset signal. One of the clever things that this circuit does is instead of using a separate clock to determine how long the counting should take place, it just uses the AC line. And what it's actually using is the high voltage source, which is half wave rectified and not filtered, so it's ideal. You still have a nice half wave pulse here, and that's applied to this voltage divider, which is a fairly high value on the top to a low value. It's 100 to 1 voltage divider, so it takes whatever the high voltage is here and divides it by 100, and that fairly low voltage is applied to 7400 series NAND gate with one input tied high, which means it becomes an inverter. And so every time the AC waveform makes a positive cycle, it's above the threshold, then below the threshold of this inverter, so the output turns one way and then the other. You get a pulse in sync with the AC waveform. And then it's inverted again through another stage, and this becomes a reset signal that's used way back here. It's basically the clear signal for the entire analog to digital converter. Then the output of that is presented through a coupling capacitor, which is fed into another inverter, but it's wire-ored with this circuit, which is a power on reset circuit. So every time the meter's powered up or power cycled, you'll get a pulse here. You'll also get a pulse here through the capacitor once every cycle of the AC wave on the power line. So you get essentially a master clock here, and that's presented in its undiluted phase as a positive going reset pulse to these two counters. And then it's inverted by the final stage of this quad NAND gate, and so now you have an upside down or inverted reset pulse, which is used to reset these two flip-flops here. So this whole string of counters and flip-flops gets reset at the beginning of every AC wave, 60 hertz or 50 hertz. If you're in a place that has 50 hertz, you can adjust that out by adjusting the frequency of the clock. But that's what that's doing. It's all just there to clear the analog to digital converter so it can start a new conversion cycle, and in preparation for that it also resets the counters so they can start counting up from 0 once the analog to digital converter starts doing its thing. Okay, now let's look at the clock, the master oscillator. This is a classic bistable 2-transistor oscillator circuit if you ignore this transistor. It's just 2 transistors with a resistor. These are NPN transistors with a resistor from positive power supply going to ground, and then they're cross-coupled. The bases are also tied high through resistors, and then the collector of this one goes through a capacitor to the base of this one, and the collector of this one goes through a capacitor to the base of this one. And that just causes them to oscillate back and forth. This one's on while this one's off, and then it's vice versa. This one's on while this one's off. And we tap off of that here and generate the clock signal, which goes into the beginning of the counter. By adjusting the resistor value on one side of this, we can generate the frequency that it oscillates. And because of this resistor here, it limits the range of this, so it's pretty much correct all the time, and all you do is fine-tune the frequency, and that's primarily just for general calibration, but it also allows you to compensate for the master clock being running at 50 hertz or 60 hertz depending where you are in the world. So you have a clock that's going here, you count up the pulses, and you can't count them any longer before the time comes around with the next AC waveform when you're going to reset the circuit and start again. So right off the bat you've got a maximum count. This is fixed frequency. You have a fixed amount of time to count. So if you did nothing else, every cycle of the AC wave, it's going to count up as high as it can essentially, and then reset and do it over and over and over again. So what the analog to digital converter does is it stops the counting early and stops it at different points early depending on what the signal being measured is. So you get a larger or a smaller count every 1/60th of a second. So let's look how that works. We have 2 flip-flops here built out of NOR gates. This one's a flip-flop, this one's a flip-flop, and the way this works is if you produce a momentary positive pulse here, this output will turn off and this output called Q will turn on. And it'll stay that way then regardless of what you do here. This one works the same way. If you produce a positive pulse here, then this is off and this one's on, and it will lock in that way and stay until you reset it. Both of these have a reset input, and they're tied together, and it comes down here. So guess what it's driven by? It's driven by this master clock that's tied to the AC waveform. So at the beginning of the AC waveform, we start the entire cycle. We reset the counters, and we reset these two flip-flops here, making them ready to operate. Now there's a bunch of resistors out here, and it's not as complicated as it really looks. Heathkit could have used logic gates here, but they cheaped out and they used resistors to form a wired OR. That's what these two resistors are. So it's acting like a 2-input OR gate with the output being here. And likewise, these two resistors are acting like a 2-input OR gate with the output being here. And then the remaining resistor here is just a coupling resistor. So when we get our reset signal coming in here, both these flip-flops are turned off. So now this point is on and this point is on, and the Q points are off. That couples down here. Remember, this is off. So it couples down here, goes through this resistor, and it turns this transistor to its opposite state. Meanwhile, this one here, which this is, remember, this is on and this is off, that couples through this wired OR gate down here, and this being an NPN transistor, this NPN transistor is turned off when its input is off. And this transistor here, by shorting out the base of this transistor, can stop the oscillator. That's what it's for. So you could have done this with a gate. If they wanted to put another gate in here, they could have left the oscillator running all the time and just gated its output from this control signal. But instead, they decided to save an IC and just actually force the oscillator to stop when it's not required, and thereby save a logic gate. Let's see, so where are we here? This is off, also is wired OR, and this NPN transistor is also turned off. Now when we get the clock signal here that resets everything, we're in a state where this transistor is off and this transistor is on, which turns this circuit on and turns this circuit on. This is a constant current source. It's very similar in many ways to the constant current source used for the Ohms function, except it's using an FET. And with an FET, the way you get a constant current source is you just tie a resistor from the source to the gate and adjust the value of that resistor, and then you get a constant current from the drain, or the drain through the source, through the resistor, and then out. And it uses that kind of like feedback. So you basically have a constant current going like this. And with this transistor turned off, having all this other stuff having just been reset, this constant current here is allowed to charge this capacitor. Previously, when this transistor was turned on, it was shorting this capacitor to ground through this low value resistor, holding its voltage at 0. But this transistor is now turned off as a result of resetting these flip-flops, so now the constant current source can charge this capacitor. If you charge a capacitor with a constant current, you get a linear ramp voltage. It just goes up at a nice straight line like that instead of having a curve to it. And a couple things happen. There are two comparators here. You might not recognize them as comparators because we're used these days to doing comparators with op-amps, but you can use transistors as comparators. And that's what's happening here, and that's what's happening here. Let's start with this one. As this voltage starts to rise, and it rises above the base to emitter voltage of this transistor, it turns this transistor on. And with this transistor turned on, it pulls the base of this transistor low through this one and through this one to ground. So a PNP transistor with its base low is turned on. So now we conduct from plus 15 volts and go out here and drop the voltage to ground through this zero calibration pot. So this is the path here, and you develop a voltage across half of this potentiometer to ground. That voltage looks like a waveform that was zero and now goes high. So it's a rising edge, and that's what's needed to trigger this flip-flop. When this flip-flop gets that rising edge, it flips, so now this point is off and this point is on. What does that mean? That means the clock has started, essentially. This point is on. I'm sorry, this point is off. So we go through our circuit here, and this is off. And that turns off this transistor, which kills this circuit, which kills this circuit, and now this pulse goes away. So that's why it's now a rising and then falling edge one-shot type of pulse. So this flip-flop is no longer being commanded to do what it originally did, but it's still holding its state because it's a flip-flop, but it's not receiving the command anymore to start the counting. But still the output remains zero, and as I said before, it has that effect looping around here to create a one-shot starting at the point where the ramp on this capacitor has got above, the 0.6 or 0.7 volts of the base to emitter voltage. Now simultaneously, the ramp is continuing upwards from, say, 0.7 volts, and the way this transistor is configured, it has an input going into its emitter, which you might think wouldn't work, but actually it does, because the bipolar transistor will turn on whenever its base is 0.7 volts more than its emitter. Well, the emitter here is a varying voltage because it's the input signal, which is an unknown. But the base is constantly increasing in voltage. So what it's doing is, let's say you had 1 volt here. The ramp is going up from 0 volts. It reaches 0.7 volts. That starts the count. The ramp continues up, and when it reaches the point where the base is higher than the input voltage, then it turns this transistor on. When this transistor is on, it pulls the base of this guy low, which turns it on because it's a PNP, and now it conducts through this resistor and through the half of this resistor to ground, developing a voltage across this, and that looks like a rising edge waveform that we're calling stop, and it has the same effect on this flip-flop as the start did on this one. It flips at the other state, so now this is off and this is on. And what effect does that have? Well, the first thing it does is it reaches around here through this wired OR, and it turns this transistor on, which shorts out the capacitor, and that ramp that's been rising, now it's shorted and it just drops back to 0. Well, that, of course, turns this transistor off, which turns this transistor on, and you essentially kill this signal. So now you've got a flip-flop that said, okay, we've started the clock, sometime later the rising ramp met the voltage in question, and then we flipped the flip-flop here and stopped, or we want to stop the clock so we're not counting anymore. And how does that happen? This point comes on, it goes through this wired OR, and it goes down here, and it turns this transistor on, which shorts out the base of this transistor, thereby stopping the oscillator, and therefore the counting cannot continue. So to recap, at the beginning of the AC waveform from the power line, we cleared all these counters and flip-flops. We cleared these, which allowed the clock to start running, and thereby counting to start as soon as this reset pulse went away. And at the same time, we allowed this constant current source to start charging the capacitor, and we also turned off this transistor here in such a way that it allowed this circuit to work. So it enabled this circuit to start. We've detected at what point the input voltage crosses the ramp, or the ramp crosses the input voltage more accurately. And at that point we flip down here, we stop the clock, so we stop counting. And until the remainder of the AC wave, we do not count anymore. And then once the AC wave starts a new wave, everything resets and it starts again and counts up again with a fresh count. So the meter is able to refresh itself 60 times a second, assuming you have a 60 hertz power line. Let's see, so we end up with a count in here, and it's going to be a greater count if you have a greater voltage coming into the analog to digital converter. It's going to be a smaller count if you have a smaller voltage coming in, because it takes longer for the ramp to meet a higher voltage at this transistor. The reason for this circuit being done the way it is, instead of just starting the clock right away, is it allows this transistor, which doesn't turn on until you get 0.7 volts above the input voltage. You actually don't start the clock until the voltage is already raised that high, because it's at that same point at 0.7 volts up in the ramp that you turn this transistor on and start the count. So that's what that's doing. It's removing the effect of the base to emitter voltage drop in this comparator circuit. So I think, let's see, I think we've covered the analog to digital converter. Now the zero adjust on here, where you decide zero is between starting and stopping, that's why this resistor is adjustable, because these flip-flops react to a specific threshold voltage, and by adjusting the resistance on this point and this point to ground, you can skew how much the voltage here and here has to move before it develops enough voltage across the two halves of this potentiometer to reach the threshold voltage of the flip-flops. And thereby you can fine-tune when it starts and fine-tune when it stops. One's going to affect the other one in the opposite direction because you're using a single potentiometer to do it. When you go in one direction, it increases the drop on one side and lowers it on the other. So essentially it's taking those two set points and moving them up and down relative to the ramp voltage and the timing. And that's how you can establish where zero is for the purpose of the entire meter. So that's pretty clever. This is actually what many people who study this circuit comment on. This is apparently a unique Heathkit design that nobody else used. It's really clever. It works quite well. Minimum parts count. All the parts are dirt cheap. And, you know, it's a good design for what it is. It's not really adequate for something that requires higher speed, perhaps because it's AC line synchronized, or higher accuracy, but for a meter that only has a 2.5 digit resolution, this is more than adequate. It does the job, minimum of parts. A little hard to understand perhaps at first. So let's finish up the circuit analysis here. So I'd said before, we build the count 60 times a second and these two counter chips and one flip-flop to get up to a count of 199 maximum, or an overrange. And as I said or hinted at earlier on, the circuit here has an overrange indicator, but once it gets overrange, it doesn't stop the count. There's still more time after it reaches an overrange before the AC waveform completes and stops. So you end up with a bogus number left over in these counters once you get an overrange. It's not always the same number. It's usually about the same number, but it's not consistent, and it doesn't reflect the actual reading because it's overranged. Modern meters tend to blank the display in that condition, or just say overrange and not show you a number. This guy just sort of freezes with a bad number in the counter, but an overrange indicator to tell you it's bad. And then these are decade counters with BCD outputs, so they're binary, but they can only count from 0 to 9. And then that BCD information is applied to the BCD inputs of these 7441s, which are BCD to 10 converter chips. So you apply your pattern of 0 to 9 binary, or BCD, which BCD stands for binary coded decimal, by the way, which is why it only goes up to 10. But since it starts with 0, it really is 0 to 9. It takes those 10 possibilities and turns on one of the 10 outputs. So you get a 1 of 10 result from the number that's coming in. And that corresponds to the 10 digits, 0 through 9, that each Nixie tube can display. Now, in addition to being a BCD to 1 of 10 decoder, these are also open collectors with a fairly high voltage capability. There are some other converters of this type that are not open collector or cannot withstand the higher voltages, but this chip can actually stand a fairly high voltage at these open collector outputs. And so what we have here is the high voltage from the high voltage power supply down here. In other words, it's sort of saying this is not a vacuum tube, there's a gas in this tube. And Nixie tubes just work by, when you apply the voltage to them, insufficient voltage, whichever cathode plate is the one that's energized will be surrounded by that nice neon bulb orange glow, and that's how you get the display. Now there's a subtlety here. how do we not have these digits rippling around and making a blurry mess most of the time? Because remember, it's only counting for part of the AC waveform before it overranges. And during that counting, these counters are going brrrr, you know, and they're rolling up really fast like a fast spinning odometer on a car. And you don't really want to see these digits rippling. Now, you wouldn't see them because it's so fast, but it would seem like a bunch of segments are on at the same time, and it would look like either they're all on or it would just look like a ghostly mess. So how does that get avoided? Well, what they've done here, and it's a sneaky thing, it's not immediately apparent by looking at the circuit, the timing here and the resetting only really uses half of the waveform. So during the first half of the waveform, let's say the positive or the negative half of the waveform, you've got these things reset here and the counting going on. And then after you get to the point where you're in the second half of the AC cycle, and now it's a positive voltage, and remember it's a half-wave rectified voltage here, so it's a nice clean half of a sine wave applied to the high voltage source. There is no power applied for the other half of the AC cycle. It's not, there's no capacitor here to provide voltage and current during the other half of the cycle, so it's totally dead on the half of the cycle. And that's how the digits get blanked here. There's just no power to power the Nixie tubes. Everything else is working, and these are in fact rippling very fast during the counting part, the analog to digital conversion and the counting. And then after that's get done, and you're now in the positive part of the AC waveform, now there's actually power applied to the Nixie tubes, and they can actually display what finally ended up in these counters. So that's a subtlety of how they managed to do a poor man's display blanking during the part of the count when you don't really want to see it on the display. Okay, looking very briefly at the IM1202 schematic, again, it's really just a copy of the 1202 schematic with a few small tweaks. The major tweak, as you can see here, there's a lot less going on in this area because there are fewer gangs of the function switch, and there's no switch for reversing the polarity. All four gangs of that switch are missing, and there are no two neon bulbs to indicate whether the polarity is positive or negative. So all of that went away. The resistors, the extra gangs on the switches went away, cost-saving measure. Now the operator has to figure out when he's got the leads incorrectly connected polarity-wise and swap them rather than just flicking a switch. Maybe not a big deal, but today we're used to auto-ranging and auto-polarity on meters. They'll just do the reading regardless of polarity, and it'll tell you if it's positive or negative. So this is a little more old school here. Otherwise, it's really the same circuit. There are some subtleties like, let's see, where is it? Just due to the different circuit board layouts, the 1202 is a little cleaner than its 1212 version, but it's the same circuit. The difference is that the 1212 uses one circuit board with all the analog on one board and all the digital logic on another board, whereas on the 1202 there are two circuit boards, one with all the digital logic and the displays, and the other one with all the analog logic. So the A to D converter, the AC converter, the constant current source, and the power supply is on the main board, and then all the digital logic is on the other board. So there are all these inter-board connections which are present on the 1202, which are not present on the 1212. That also probably provided a bit of a cost savings for Heathkit, because they didn't have to have as complicated a circuit board. Also made it easier for the kit builder because the 1202 is kind of a pain and everything's jammed in real tight to fit in that case. Anyway, but it's the same circuit. Couple things down here on the output of the the AC converter rather. It's a double RC filter on the 1212, whereas on the 1202 it was a single RC filter. So they may have decided that the 1202 was a little noisy perhaps on the output of the AC converter, so they added an additional pole or stage to the filter. It really only added one cheap capacitor, everything else is the same. The circuit here is just the same. Circuit here is just the same. You know, the only real cost savings they had was dropping the polarity switch, adding one capacitor, there's a cost increase, and doing away with the extra 2 neon bulbs and their associated resistors for the polarity indications. Otherwise, it's just the same thing. Same power supply exactly. Okay, finally getting to the IM1210, the final meter in this series. Looks an awful lot like the other one, but there are differences, so I'm going to try to cover those without going into great detail again. I'm going to try to focus on the differences. Once again, it's a single circuit board, so there are fewer interconnects between boards. It's the same circuit design down here for the 5-volt power supply. Same exact design, except instead of using a possibly harder to get or more expensive power Darlington transistor for the pass transistor, they just use more pedestrian high power and low power single bipolar transistors, still connected in a Darlington pattern, but doing the same thing. It's just probably a little cheaper for the part. The power supply for the bipolar supply is a little different. In this case, you know, let's look back at the other guy. The one side of the secondary was going to the minus 15 volts, and the other side of the secondary was going to the plus 15 volts, granted with a half-wave rectifier and a dropping resistor, and then the ground was established by the 2 voltage dividing and regulating Zener diodes so that they'd be centered around ground. Now it's a little different with this supply, although it accomplishes the same thing. This side of the supply is just connected to ground, and there's still the half-wave rectifier here for the plus side, but there's a different half-wave rectifier for the minus side, which is what you have to do if you're not going to use this side of the transformer for the negative side. So it's just 2 different ways to skin the cat. It takes an extra diode, but and it also necessitates having another dropping resistor on this side, because it's not just a single 30-volt supply that's split in the middle to get a ground reference. This is actually a positive regulated supply with a filter cap and a regulator, and a negative rectified supply. I may have said regulated up here, I meant rectified. A negative rectified supply with its own filter cap, dropping resistor, and Zener diode regulator. But the result is still a plus and minus 15 volts. We're also using that same secondary to develop the AC sink. You may remember on the other meters, it was the 3rd secondary, the one for the high voltage, that was used for the AC sink. That winding isn't even here on the 1210 because there is no need for a high voltage supply. Instead, they have to get that AC synchronizing signal somewhere, so they get it off of a 3rd rectifier off the same secondary here, and that goes to the AC sync source. But we're still developing an adjustable AC reference test point the same way we did on the other design for use in calibration. Now, something I didn't cover on the other ones is we can calibrate AC and DC using the test points that are built in, but for testing and calibrating the ohms, all of the models have the same 5 precision, 1% precision resistors on the board, which you tie into and then adjust their relative or respective trim pots for each range to calibrate it. So that's common on all of them, and I hadn't mentioned it when I discussed the other 2 circuits. The 1210 only uses 2 jacks. You don't have to move the leads around anymore when you go from voltage to current or voltage to ohms reading. It's all done within the switching now. It still has a fuse, and immediately you're presented with the master function switch through which everything else goes. For AC and DC volts, it's applied to a resistor ladder voltage divider to knock the voltage down to an appropriate small range. And something the other ones didn't have is it has a couple of stabilizing capacitors across these 2 resistors. They didn't have that before they added it here. A small refinement. For current, whether AC or DC, we come up here, we apply it to this switch, and we have a resistor ladder here. Now on the other design, it actually used 1 shunt resistor, a different shunt resistor for each range when measuring current. Here, it's using a resistor ladder for the shunt. Achieves the same goal, just does it a little differently. And then the current returns to the negative input and circuit ground. At the same time, we develop a voltage across this shunt resistor, which is tapped off here, and depending on whether you're measuring DC volts or DC milliamps, it's further routed and conditioned. If you're measuring AC, it gets routed to the AC to DC converter. If it's DC, it goes straight through, and everything ends up at this final selector switch on the function switch, which goes into the analog to digital converter. The AC to DC converter is really the same design as on the other 2 models, but they've cost reduced it. It has the same basic circuit layout, but here they don't have it limited to plus and minus 5 volts. It's just clamped to plus and minus 15 volts. They don't have the more elaborate bias circuit for the buffer FET. It's just a simple resistor to ground. The op-amp circuit is identical, except on this capacitor they're not using an electrolytic or a tantalum. They're just using, I don't know, a mylar cap or something. But it still works the same way. And whereas on the 1202 and the 1212, there was this extra resistor right here, like the 4.7K resistor. That's a range limiting resistor for the calibration potentiometer. So a larger turn of the potentiometer has a smaller result in the parameter you're trying to calibrate. When you take that resistor out, the pot is no longer range limited. So now a smaller change on the pot makes a bigger effect in whatever you're trying to adjust. In this case, the AC calibration. So by losing a resistor and cheapening the kit by a few cents, it just makes it harder to calibrate. That's the upshot. It retains the 1212's double filter, RC filter. The component values are different too. They tweak that a little bit. The oscillator is really just about the same, but they've improved it. It still uses the resistor to pull one side of the oscillator low to stop it, but they've added a few refinements. They added 2 diodes here and 2 diodes here. Their temperature coefficient is opposite the coefficient on the transistors, so this is essentially the resistor transistor circuit is compensated by the reverse temperature coefficient of these diodes, let's say it that way. So by introducing those, it makes this circuit more temperature stable. That was one of the things that always had to warm up on the 1202 and the 1212. When you first turned it on, they recommended you leave the meter powered for half an hour before you start taking measurements or calibrate it, because the readings would be off. Maybe not seriously, but they wouldn't really stabilize and reach maximum accuracy until it warmed up. And I think that's part of what they were trying to do here, was try to improve that, make the circuit more temperature stable. They also used different models of transistors here. They tend to use more of the same model of transistors throughout, whereas on the other ones they had quite a few different models of transistor, and they reduced the number of parts they had to stock in order to build this. There's also an extra diode in here, which helps this part of the circuit work better. I won't go into the reasons why. But once again, it generates a adjustable oscillator or clock frequency. Once again, it's adjustable up here. And the output still goes to the counting input of a bank of 7490 counters. Except here there's a third one, so they actually are using a third decade counter chip instead of a couple of flip-flops, as they did on the other models. They replaced these two flip-flops with another decade counter chip. But that works because if you actually look inside these 7490s, what's actually in there is like 4 of these. This is a 2-stage ripple counter, and these are 4-stage ripple counters. So they're essentially wiring it up in such a way that it acts like the 2 flip-flops rather than acting as a counter exactly in the way these other ones do. So it performs the same function. Instead of using 7441 BCD to 1 of 10 or encoder or decoder chips, they use 7447 chips, which are BCD to 7-segment chips. So they're designed for driving 7-segment LEDs. You've got your 7-segment LEDs up here, 3 of them. So instead of using a neon bulb to cheat and get the highest one in the hundreds position, they're actually using a legitimate third 7-segment display. And to get the one, they have to turn 2 segments on, segments B and C, which are these 2 segments here. So that looks like a 1. And they're just driven off of one of the outputs of an internal flip-flop. Then the overrange indicator is handled similarly. It comes out of another internal flip-flop and drives segment F, which is this segment up here. And on the meter face, there's an arrow pointing at that segment that says overrange. So that's how we're getting the overrange and the 1 in the hundreds position on this model of the meter. But otherwise, it's basically the same design. Now, the Nixie tubes did not need current limiting resistors, but LEDs do. So you have all these resistors added here for current limiting on all the segments of the LED display. And this is not a scanned or matrix arrangement, so all these are on all the time. More modern designs might turn one on at a time and change the pattern, but here everything's just driven all the time. However, we still have a common anode on each LED digit, and where does that come from? Comes from a half-wave rectifier off of the AC line. So it still uses the same trick that the other models used to blank the display while you're counting, and do it without using any extra ICs. All you're doing is throwing in a 1-cent diode and accomplishing the same thing, just cheap and dirty, but it works. The line frequency pulse shaper, which was done with 4 NAND gates on the older models, was replaced by a somewhat different circuit on the 1210, although it does the same thing. On this one, there is no power on reset. It was somebody wised up and realized you didn't need it. When you're resetting the circuit automatically 60 times a second anyway, why do you really need to reset it once on power up? Nobody's going to see the garbage it does on the first cycle before the line frequency resets it. I added this diagram here to further illustrate what's going on with the AC waveform. So on the plus waveform, it's displaying, and that's the only one that has power through the diode. On the negative side is when it's doing the counting. So that was implicit in the other schematics, but I didn't actually illustrate it. And Heathkit only bothered to illustrate it on their schematic for the 1210. So I did likewise here. There's a note here that describes that bit about half the voltage is half-wave rectified and used to provide the current to the display, and is blanking the other half-wave just so it's less, or it's not intuitive either way, but it's explained here, whereas I didn't explain it on the other ones. Because the way they did it here, there's more spare room, so I could put a drawing and a note in here that I couldn't really afford on the other ones. This circuit, once again, takes the AC sync coming from, where did I get it from? Oh yeah, down here. The AC sync, half-wave rectified, off the transformer. And it's applied to this voltage divider. And again, the voltage is going up and down here. And it's clamped, so it can only be low. It can't go very high, because if it is, it's shorted out to the plus 5 volt rail. So it limits this voltage by action of this diode. Then it's applied to the input of this inverter. Instead of the NAND gates, we have a hex inverter IC, 3 of which are here, and the other 3 are up here acting as drivers for the third digit. As the signal here goes up and down, it's either above or below the input threshold of this IC, and so the output is essentially a square wave going up and down here, and then it wraps around. I didn't check to see if the this is a 7416, I don't remember offhand if that's an open collector IC or not. It might have open collector outputs. There are certainly pull-up resistors on all outputs, which makes me think that it might be open collector. Or they might just be there to give it a snappier action. Anyway, so when this signal rises, then this signal drops, and it's inverted, so this signal rises, and that's capacitively coupled back around to the input, which I think that makes it act a bit more like a Schmidt trigger, kind of. It makes this have a more positive snap action to the detection of the half wave here. What you end up with is a signal here which is in sync with the AC wave, but it's like a square wave. And that's applied directly as the clear signal to reset these two flip-flops, just like we did on the other ones. Same exact thing. And just as we did on the other one, we would take that signal and invert it again for resetting the counters. And that's what's done here. It's capacitively coupled, so it shortens it, where this is a signal that's on for half a wave. This RC combination here shortens that pulse to a very short pulse, which comes out of this final inverter. So you end up with a brief reset pulse at the beginning of each waveform, and that resets all these counters. So, works just the same. It's done with a different circuit here, performing the same exact tasks. Let's see. To control the decimal points, on here, because where the decimal points are located, on the Nixie tubes, they were on the left of the Nixie tubes, but on these LED 7-segment displays, the decimal points are on the right, and we don't need a decimal point at the far right, so it's not connected. Instead, we're using the decimal point on this guy and the decimal point on this guy in the way that the Nixie tube ones use the decimal points here and here. They end up in the same position relative to the digits. Finally, let's look at the analog to digital converter. It's really the same topography. It has the same exact flip-flops for starting counting and ending counting. It has the same 2 wired OR gates here done with resistors. These 2 are 1 wired OR, these 2 are another wired OR. Works exactly the same way. It still has the 0 potentiometer for skewing the voltage drops up and down, thereby adjusting where the counter thinks 0 is relative to the ramp. But they've replaced most of the components in here with different components. This part's pretty much unscathed, except they did leave out a second resistor here, which was a range limiter for this calibration control. So now it works the same way, but this is touchier. Instead of being able to move the pot over quite a range and really dial in, you're sitting there just breathing on it, trying to get the right adjustment, and if you breathe a little too hard, you go past it. So it's more frustrating to calibrate it, and probably less reliable in the long run because the pot is so tightly scaled. But it has the same exact resistor or transistor pulling down the capacitor here. The capacitor charges up the same way. It has the bipolar transistor acting as a comparator between the ramp voltage and the input voltage. That's exactly the same. But on this one, we invert the signal with a single transistor. From this transistor, we invert it with this and then send it out here as the stop signal. On this one, it's using a Darlington pair. So it has higher gain, and thereby it is faster reacting. It's more of a snap action. So I guess I'd say it makes the circuit less fussy. Just a little tighter operation probably is a good way to describe it. But otherwise it's exactly the same thing. And similarly, we have this transistor which detects when the ramp has crossed the emitter to base threshold of the other comparator, and then tells the count to start through this inverter. And then there's this transistor which can turn this circuit on and off so that you get a pulse for the start instead of just a steady on signal. Really the same thing is done here, except instead of the second transistor, they're using a diode to effectively turn this comparator circuit on and off. It's doing the same job, and instead of the single inverter transistor here, it does the same as here. It uses a Darlington pair to get a snappier, more positive action. And in that way, it's exactly the same as the other design, just some different components doing the same jobs. Now here's where the final subtlety comes in here. I mentioned before that they snuck in an extra indication on the display. On the earlier designs, if you had a negative input, if the polarity was reversed, the voltage mode, if you had the polarity backwards, or the current sensing mode, if you had the polarity backwards, you're going to present a negative voltage up here instead of a positive voltage. And this circuit doesn't really know what to do with that. However, remember that this transistor turns on when the base is higher than the emitter. And normally that would happen after you've started the ramp going up on this capacitor. But what happens if you make the emitter negative? Now it's always on. Doesn't matter what the base is, whether the ramp is high or low, whether the ramp is even operating. This transistor is always on, which is always telling the flip-flop to stop without ever having started. So this circuit cannot work correctly when you have a negative input. even though the clock is still running, because these flip-flops have been reset by the AC waveform coming in from the line voltage, it's getting bogus control signals here, and as a result it gives you garbage on the display when the input is negative. Well, that hasn't been fixed on the 1210, but what they figured out was by doing one little thing, by putting a capacitor here and slowing down the response of the start slightly, they could detect when the start and stop signals aren't working correctly in relation to each other. And it uses that to advantage up here. When this is on here, it turns on the base of this transistor, which turns it on, and it provides a path for the G segment of the display, which is the middle one, which is the one you'd want to show a minus sign in front of the 1 or in front of whatever's to the right of it. But that by itself doesn't turn it on because you need a path to ground from this emitter, and that only comes from another flip-flop in this package. And that flip-flop is synchronized to the operation of the rest of the circuit. And without going into too much detail, by having this point be on at a time when this point is low is essentially detecting an illegal situation. This point here should never be low until after the count is started. So if you get this condition here as a result of a negative input while this output here is low, now you've created a condition where you must have a negative input. That's the only way it could happen. And now you actually create a current path through the G segment, through the current limiting resistor, through the transistor, and through the QA internal flip-flop of this counter here. So that's how the negative is detected. It's just detecting a anomaly in how this circuit works whenever it gets a negative input, detecting that and then causing the minus sign to appear. There's really nothing happening to correct the garbage on the rest of the display, but at least it lets you know that you've got a negative input, so don't believe the number you're getting. So I think that is my lengthy walkthrough. This is probably all added up to be the better part of an hour, but I hope it's interesting.